Hi, this video is to help you understand how to perform the experiment determination of the canola oil water partition coefficient. It's not meant to replace the procedure, it's just meant for you to watch before you do the procedure so that you better understand what some of the steps are asking you to do. Today we're going to be using a very specialized piece of glassware known as a separatory funnel. And a separatory funnel has a design that it makes it very useful when we want to mix together liquids that don't combine, like oil and water or organic solvents and water. And we can shake them up and give them a chance to react or equilibrate together. And then because of the shape of it, we can drain off one of them from the other by opening up this valve here on the bottom. The first thing that you have to do is to mix together 100 milliliters of oil and 100 milliliters of canola oil. My separatory funnel is a little smaller than yours, so I'm only going to do 50 milliliters. But when you do the experiment, you're going to do 100 milliliters of each. Okay, so there's 50 milliliters of water. I'll make sure my valve is closed. It's perpendicular to the direction of fluid flow. And I'll put that in there. It's a good idea to have a container like a large mug or a pot around to stand the separatory funnel up, like you see me doing there. All right, and that's about 50 milliliters of canola oil. Okay, and you guys can be doing 100 milliliters of each. Okay, and we'll do what people often do with separatory funnels: put the penny head stopper on and give it a good shaking. All right, you should shake for several minutes, so I'm going to pause the video while I do that. After several minutes of shaking, you'll see it looks very milky, very cloudy. And at first, you might not see that there are separate layers in there that are forming. But if you let it sit for a few minutes, as they tell you in the procedure, after about 5 or 10 minutes, you will see the two layers reform, like I'm showing you here. All right. After you've done that, we now have equilibrated the two components together. So a small amount of oil dissolves in water and a small amount of water dissolves in oil. And we'd like to work with solutions that have those equilibrated, saturated amounts in them. So that's what we've just done. We prepared an oil and water layer. They're each saturated in each other. So what we want to do is use the separatory funnel to drain each one of them off to use in the later parts of the experiment. Okay. So again, 2 clean 100 milliliter containers to drain off those layers into. You have to take the stopper off, otherwise the solution will drain, air can't get in, and start draining the water layer off into the first. The shape of the separatory funnel comes to a point here so that you can fairly precisely control the volume that goes in there. When it gets down to that point, you want to have your hand on the stopcock to stop it. Okay. Very much before you see the liquid layer, the next liquid layer upcoming. You may see some emulsion layer also. You may see a third layer that exists between the two. You don't want to draw any of the emulsion up with either one of the layers you take out of here. So this I'll put on the side. This is my aqueous layer. I'm going to be working with that in the next part of the experiment. And I also have to collect the oil layer. But before I do that, I want to wash the emulsion out of the separatory funnel into the waste container. So make a waste container with a coffee cup at your station and drain off beyond where you see the oil go through. So I just drain some extra oil through to wash that off. Okay, now I'll drain the rest of the canola oil off here, and I know I won't have drawn any of the emulsion up. This takes a while to drain, so I'm going to pause the video. Okay, I finished draining off the oil layer. Now these two solutions I want to put on the side. These are the saturated canola oil and water solutions that we're going to use in the next parts of the experiment. The next thing that we have to do is a preparation for next week, which is to mix together a small amount of both the canola oil, the water, and the triethyl citrate in this separatory funnel and allow it to equilibrate. That equilibration we want to be able to sit for a week. So we're going to prepare that this week, but we're going to leave it sitting until next week. Okay, so for this equilibrated mixture, we need to make sure the stopcock is closed, certainly. We want to measure about 15 mLs of the canola oil. Okay. Put that in the separatory funnel. And then we need to measure about 15 mLs of water. That's just about 15. And then put 15 drops of, I'm going to do this whole demonstration with acetone, but you guys will be doing triethyl citrate. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 drops, 15 mLs, 15 mLs, and 15 drops. Put those three together in the separatory funnel. Give that a good shaking for several minutes. And this we're going to leave sitting to equilibrate until next week. The triethyl citrate is an emulsifying agent, which means it will form an emulsion layer between the two, and it will take much longer for the oil and the water that are not going to be part of that emulsion to separate. So we want to let this sit for a full week. So set this up somewhere where it's not going to get knocked over in your house, and we'll get back to that in the second part of the experiment. Now, in the next part of the experiment, you have to prepare a number of standardized solutions. And this procedure that I'm going to demonstrate briefly, you're going to do for both water-based solutions and oil-based solutions. Each one of those is going to have a whole set of solutions that are prepared. The first solution for both of them is the solution that has none of the triethyl citrate added. So when you label a tube number 1, you just put a little bit of the water on the side when you're doing the water-based solutions, and a tube number 1 similarly that's labeled for the number 1 for the canola oil, and you put it on the side. And then the other tubes have specified amounts of drops. So we want to measure the percentage by mass of these solutions. Some of the amounts of drops are too small for the scale to register, and we're going to figure it out from our calculation from the earlier part where we figured out the mass per drop. But the procedure in all cases is take a little bit of the, you guys will be doing triethyl citrate, I'm doing acetone, and put the amount in the table. So I've zeroed the scale, and it says to put 1 drop in for trial number 2. So I put in 1 drop. 1 drop may or may not register on your scale, but whether it does or not, we know that 1 drop is added, and we can figure out its mass from our earlier work. Then the other part is to add the solvent. In this case, we're going to do the water-based example one, but you'll also do a set with canola oil. So for all the solutions, after you put the number of drops that's in this table for that tube, then you'll just add the solvent. In this case, we're doing the water-based ones until you have a total mass of around 5 grams. That'll be somewhere between 1 and 2 full droppers. I think that's close enough at 4.99. Then that would get recorded in the data table here. Okay. That is the total mass of the solution that's in there, and with our calculation of the mass of the drop, we'll be able to calculate the mass by percent of the triethyl citrate, or in my case, acetone, that's in that solution. So prepare a total of 8 of those solutions that are water-based, and then you'll follow the same basic procedure, creating oil-based solutions, switching to adding this as the solvent, adding this number of drops of the triethyl citrate, and recording the total mass after you've adjusted to be about 5 grams. Hi. Now, in this experiment, you do measure out the amounts of the triethyl citrate by drops, but we want to know the masses that those drops have. The reason we use drops is that some of the amounts are too small to directly measure the mass on the scale. So that's why in this part of the experiment, we have to figure out the mass per drop. So throughout this experimental demonstration, I'm using acetone, but you would do this part of the procedure with your triethyl citrate. So what you want to do is get a Dixie cup or a 100 milliliter plastic container with a screw lid, and use it to stand up a 15 ml test tube. Turn on your scale. It ought to read 0. If it doesn't, you have to tare it. And then you're going to take a clean dropper and count out 100 drops of the triethyl citrate. I'm doing it for acetone. So I'm going to pause the video while I count up to 100. Okay, so I counted out 100 drops there, and that 100 drops mass would go here in the data table. For me, that would be acetone. But for you, you would write down the mass of your 100 drops of the triethyl citrate here. So I measured 1.74 grams of acetone for 100 drops. Or if I just move over the decimal place or take out my calculator, that means 0.0174 grams per drop for acetone. For every one of the trials where I use a different number of drops, I can use this to calculate the mass of that number of drops. In the trial number 2, for instance, that I did, there was only 1 drop. So that would be the mass of acetone that I would put here in the data table. 4 for me would be acetone. And for any other number of drops, I would have to multiply by this factor. So for instance, in the trial where there are 2 drops, I would multiply by 0.0174 grams per drop and take out my calculator. Is 0.0348. Right? So that would be in the next trial. 8. Okay. Next thing you need to do is get out your refractometer and calibrate it. Okay. The way the refractometer works, the samples are placed on this stage here, and then this cover is gently lowered, trying to catch no air bubbles. And then you look through it with your eye like this, and what you will see, I'll show in a separate video I cut in, will be a dark and a light region. And at the boundary between the dark and the light region, you will read the scale reading that's in there. The units on that scale are known as bricks. Before you use this device, you should calibrate it, and it's calibrated with pure water. So here's an example of how a refractometry measurement is also made. Right, you can put a small amount of the liquid you're testing here. Okay. You want to gently lower the cover slip, right, keeping care to see no air bubbles. Okay. It's a little bit messy. Some stuff will come shooting out the sides. Okay. Then if you're calibrating, you want to pull this little cap off here, and there's a tiny screwdriver in here. And what you do is you put the screwdriver in there until you feel it's in the groove of the screw, and then look up into the refractometer, hold it towards the light so you can see, and you want to turn the screw, you can do it by trial and error, left or right, until you see that dark and light boundary sitting right at the 0. Water should read 0 bricks. And the reason we calibrate it is because the refractive index is very sensitive to temperature. So whatever temperature is in your room is probably not the temperature it was most recently calibrated at. After you're satisfied that it's calibrated to 0 bricks with pure water in there, then you want to clean it off. And this is a procedure you'll use for cleaning off throughout the experiment. You want to use this soft microfiber rag provided in your kit. And we don't ever wash this or fully immerse it at the sink. What you can do is just wipe it off carefully with this microfiber rag. Okay, don't use any other rags from around the house. Okay, now it's ready to go for the next sample. So you will measure the refraction in bricks for all of those tubes that you prepared. You have between 8 and 10 of them for the water-based and the oil-based solutions. Every single one of them, you'll go through this procedure of putting a few drops on the stage, putting the cover slip down gently with no air bubbles, hopefully. If you get air bubble, lift it up and try again. And reading the refraction and recording it in the data table. You'll notice there are 2 data tables because we have 2 sets of solution, the water-based and oil-based. So this is the canola oil saturated water. That means that's the water-based solution. You would be recording your relative refraction values there. And for the oil-based solutions, you would be recording them there. For the water-based solutions, you should expect values in bricks between 0 and 10. For the oil-based solutions, the value will all be in the 70s. If you're getting values that are outside that range, look to see if you've made a mistake. If, for instance, you're doing the water-based solutions and you actually have a drop of oil that's somehow gotten included. When all that data has been collected, you're going to prepare 2 graphs. Those graphs I'm going to just make rough sketches of. The graph paper has been prepared in the lab report, and you probably will see both of them varying with a certain amount of % error. One of them may be increasing, and the other one, very likely you may see to be decreasing. Both of them you should draw some interpretation of. You could draw a linear interpretation, or if you think it looks curved, the smoothest curve you can easily draw. And both of these graphs we'll be using as calibration curves, which means we'll be using them to figure out outputs from inputs. The inputs will be refractions that we measure in the very end of the experiment for equilibrated oil, water, and triethyl citrate. And the way we'll do it is we'll look for a refraction value that we measured on the y-axis for the sample of oil or water, and we'll go across until we hit the curve, and then use a ruler to make a nice 90-degree turn and go down. And the value that we read here from this input, this output, would be the percentage of triethyl citrate by mass that goes along with that refraction that we measured. So if we measure that refraction, we can figure out the percentage of triethyl citrate in that solution. Now, after a week has passed, the mixture you prepared that has the canola oil, the water, and the triethyl citrate will have mostly separated. You very likely will still see a little bit of emulsion in the middle, but this now has at equilibrium the 3 components. There is a distribution of some triethyl citrate in the oil and some triethyl citrate in the water, and that really is our goal to figure out today. We want to figure out what's the equilibrium constant that determines the distribution between those 2 layers, the canola oil water partition coefficient. So what we want to do is take samples of both this oil and water layer and measure their refraction in order to figure out what the percentage of triethyl citrate in each layer is. So I'll take the stopper off here, and I'm going to drain off some of the water layer into a small Dixie cup. And we only need a few drops for the experiment. And you should follow the same procedures you did last week to calibrate this first with water, because the temperature in the room is probably different than it was last week. And then take a clean dropper, sample some of this water layer that has the triethyl citrate in it. And again, make a measurement of that refraction, and that value gets recorded in a different data table. Okay. That value will get recorded in this table here. And I was doing my experiment for demo purposes with acetone. This experiment works very well with acetone also. And I just collected a refraction in the water layer. I saw 7.5 as the value. And I'm going to repeat the same thing in the oil layer. When I do repeat in the oil layer, I'm going to find a value of 73.8. So it's these 2 refractions that we're going to use as the inputs for these curves that we created, the standard curves. So for instance, my 7.5, I'll look on the axis here. I'll find 7.5 is halfway there in between the 7 and the 8. I'll go across with my ruler till I hit the curve. Okay, now I'll make a right turn, 90 degrees. And I read that to be about 6.6. Okay, so that means the refraction that we measured here tells us that we actually have a percentage of 6.6% of the triethyl citrate, or in the acetone, in my case, for you guys, would be the triethyl citrate in that solution. We'll do the same thing with the 73.8 on the curve for the oil-based solution here. I would find the 73.8 go across and go down, and it looks like it's about 2.5%. So in order to calculate the canola oil water partition coefficient, we need to convert these percentages that were most easily figured out as mass percentages into mass volume percentages. And the way you do that, the way you change the V in the bottom of the percentage, the M into a V, is to use the density of the solution, right? If I write out what 6.6% MM means, it's 6.6 grams of acetone for 100 grams of solution. So here I look up the density of water is out 0.997 grams for every 1.0 milliliter of solution. We're going to assume the water-based solutions have a density of water, and the density that we'll use for the canola oil is 0.92. All right, so this is now the percentage MV. Here is a similar calculation to convert the percentage of, in your case, will be the triethyl citrate. I did acetone, from MM to an MV description. We're just going to assume that the oil layer has the same density as pure canola oil. That's 0.92 grams. Finally, the calculation of the canola oil water partition coefficient, we've been abbreviating as that, which is the equilibrium constant for the distribution between the oil and the water layers. It's just the ratio of the percentages MV in each of the layers, canola oil on top and water on the bottom. Calculates to be 0.35 for acetone. That means that regardless of the particular amounts that we throw into a mixture of canola oil and water, the relative concentrations we'll find are always in this ratio.